Okay, g'day folks. Welcome to another video. Yesterday I uploaded a video, but there was some detrimental flaws as pointed out by the viewers. So I thought what I might do, instead of just putting some annotations on the video, which nobody reads, I thought I might upload another video to try and fix those flaws and maybe talk a little bit more about vectors versus lists. I'll leave the original video up because it's got some good info in it, and folks might want to know where this video came from. And if you haven't watched the original, then you might want to go and do that first because it's got a bit of introduction stuff. Alright, so one of the things that the viewers pointed out was when I said that lists are easy to sort, and that's why they've got a sort method. Well, that was complete garbage. I just made that up. The truth is that vectors are really easy to sort as well. So vectors have their own sorting algorithm in the algorithm header. Yeah, you've got a sort function, so you can pass a vector iterators in there. But for the sort algorithm, you need random access iterators, and lists don't have that. So they decided what they would do is supply sort as a method for lists. Yeah, so thank you very much, viewers, for pointing that out. That was a big flaw. Alright, and the other thing that I want to talk about was my final example. So at the end of last video we had a bit of a race of vectors versus lists, and my aim was to show that it's really fast to insert items in the middle of a list. And that's true, but only if you've got an iterator to the spot where you want to insert the item. Now, what I did was just bizarre. What I did was very, very stupid. I had an iterator. It's pretty cool. Let's have a look. Here we go. So this is the code from yesterday. This is a classic. Not in a good way. I've got a list, and I make an iterator to the 50th position outside of the loops, just here in these first few lines of code, and down here inside my loop that I'm timing and racing against the vector, I insert an item at that iterator position. I insert 10. And the next line, I erase that iterator. Now the problem is that when I erase this, it becomes invalid. Oh, yeah, just blunder. So I could have actually taken the video down, but I figured it's best just to, I don't know, make an amendment video and move on. You can't use that iterator anymore. It doesn't point to anything sensible inside the list. So straight after I've erased it and the loop starts again, right here when I insert that 10 to that position, I mean that line's no longer meaningful. Alright, so that's probably the biggest blunder that I made. And thank you very much to the viewers who pointed that out. What I should have done is created another iterator inside the loop and stepped back up to position 50 every time. So that's what this code here does. Let's have a bit of a look. Oh, a closer look at it. Yeah, I won't run it because it does basically the same thing as yesterday. Alright, so instead of creating my iterator outside the loop, this time I'm creating my iterator inside the loop and stepping it up to position 50. Oh yeah, thanks to Communist Goat Boy, you can actually use advance instead of this for loop here in ++. I think in the background it's going to do the same thing, but yeah, it's much cleaner code, so thank you for the suggestion. This will work, and it's safe. Yeah, so we're erasing the iterator just here, but each iteration of the loop, we're creating the iterator again and stepping it back up. And this is much faster than the vector. Once again, it's much faster than the vector. Okay. But it's a flawed example still, so the list vastly outperforms the vector as expected, but a few viewers pointed out that the race is completely contrived, and I'll admit that. I designed that race particularly to show that it's faster to insert into the middle of a list, and it is, but only if you've got a iterator pointing to the position that you want. If you, instead of inserting to the 50th position every time, if we do something like this, maybe pause and rand 10,000, and we insert to a random position every time. This is much more likely to occur in the real world. All of a sudden the vector starts to outperform the list. And I think that's probably because if you've got to insert an item right near the end of a vector, well, the vector doesn't have to move much around at all. It's only got to remove however many items are above where you're inserting. So the vector starts to outperform the list. I think also that if you've got to insert an item right near the end of a list, then this advance just here is very slow. You know, it's got to count through every single element before the one that you're inserting, before you can actually insert that item that you want. I mean, you could use reverse vectors, reverse iterators, sorry, and jump backwards if the item you're inserting is closer to the end. But I think, you know, the code becomes complicated, and yeah, it's probably not worth it. It's probably not worth it. Okay, so it's a very flawed example, and thank you very much to Salt Paral and Communist Goat Boy for pointing that out for me. A list is faster. Yeah, but it's not a very practical example. So the question really is, what good is a list? And I want to say, before we go too much further, that usually you want to use a vector. Yeah, almost always. Lists are almost no good at all. Almost no good at all. You could make queues and decks and stacks if you want, but they're already provided by the STL, and I think they use contiguous memory anyway, something closer to a vector, so yeah, you're probably better off not coding your own queues or stacks or whatever. Alright, but lists do have some really cool little functions provided, some little methods which we can go through now. I want to mention before we go through these that you could easily make these for a vector as well. A vector probably do it even faster. Anyway, let's have a look at what they are. So, oh, you can see up here, I've already testing one of them before. The first function method that we'll look at is merge just here. So this is really interesting. It takes two sorted lists, so say L1 and L2. Note that they're sorted within themselves, so 5, 8, 10, 13, that's sorted, and 2, 9, 11, 17, that's sorted as well. If we merge them both together and we use a bit of a for, we use a for each, another thing I neglected to mention last time, which is ridiculous. I think I uploaded a video on it like a week ago. Anyway, we can use for each to iterate through our L1 and print out the items. So let's see what happens. We should get... here we go. So we've got now a single list in L1 that's the sorted combination of L1 and L2. So that's really, really cool. Something else to be aware of is that L2 after that call to merge is actually cleared. So we could see out there here, well, the count. L2.size. Let's see how we go. Yeah, so you can see there that L2 is cleared. The size becomes 0. Yeah, but L1 is the merged sorted list of both of them. If they're not sorted already, so say we've got something here like 234, then you want to call L1.sort and L2.sort just to make sure it's sorted, then call merge, and yeah, you're laughing. Alright, so merge doesn't sort your lists for you. Okay, the next thing that we want to look at is splicing. So this is super cool as well. Once again, you could easily get a couple of vectors to do this. You just need a bit of swap space and you write as rain. But, well, it's convenient with lists. They have it as a method. Okay, so to splice is to join two lists together. This particular example places L2 on the end of L1. Yeah, so L1 will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If we just hit run, we'll see how we go. All good, all good. That's important too. So the L2 once again has been cleared. Yeah. So with merge and splice, L2 or the other list is always cleared. If you want to add an item not necessarily to the end or the start, I mean you could do this begin here. That would add L2 to the start of L1. But you can always make an iterator if you want to point to some other position. So. Just call it I, even though I've got an I down the bottom there. Yeah. Okay, so if we use I just here as our position, what we'll end up doing is sticking the L2 just here. Yeah, so I think our L1 list will go 1, 6, 7, 8, 9, 10, 2, 3, 4, 5. All good. Okay, that's splicing, but things get really cool when we have a look at remove if. Okay, so this is what I was testing before you came. This allows us to provide a predicate. Let me just change a few things around. Okay, a predicate which specifies a condition. So it takes an integer in this instance because my list is actually comprised of integers. And all this particular predicate does is just a function that returns bool. It tests if the integer is even. So if the integer is even, it returns true. If the integer is odd, it returns false. And remove if is going to remove any of these numbers that return true when passed to the predicate. Yeah, so what we'll end up with is a list of all of the odd numbers. And we no longer have L2, so I might just comment that out and run. Okay, there we go. So 57593. That's this list here with all of the even numbers removed. Very cool. Remove if. All right, next amazing thing that lists can do. Unique. Okay, so there's a couple of versions of unique. We can do the no parameter version, which is this one just here. And let's have a look what unique does. Okay, unique actually compares adjacent objects. So the 4 and the 2 and the 5 and the 7. And if they're the same, then it removes the second one of them. Yeah, so obviously none of these two are the same. Well, not obviously, but none of these two are the same. So what you want to do, if you want an actual unique list of your items, is sort your list first. Yeah, so if we sort this list just here, we'll have a bunch of 4s at the start, a few 2s before that. But the call to unique here will compare each adjacent item and remove any that aren't unique. So let's have a look. We'll have whatever the unique items are in the list. Good stuff. 2, 3, 4, 5, 6, 7, 8, 9. Good stuff. Just remember to call sort first. Yeah, because it's only going to compare pairs. That's unique. That's pretty cool. But check this out. This is even better. You can actually supply a predicate function for unique. R equal is what I've called my predicate. Let's just copy this and see what happens. Once again, I think I've got to fix a few things. Yeah. Okay, so this particular predicate here says that numbers are equal if they're within 10 of each other. So it's a bit of a made-up example, but any pair of numbers that are within 10 of each other, the second will be deleted from the list using unique. Yeah, so this is really just so that you can specify your own definition for what equality means. Yeah, maybe you want to use it to round a bunch of doubles or something like that. I mean, if you're working with floats and doubles, you'll often have numbers that are really close together, but due to rounding error in your computation, they won't be exactly the same. But you can use unique with this predicate function here to remove them anyway. Alright, so sort the list first, because once again, unique actually only compares items that are adjacent to each other. Yeah, so you want to sort it first, and if we hit run, let's see what happens. I think we'll remove a few of these items. Okay, so 172, 662. Okay, the 662 was removed. Yeah, so 659 and 662 were deemed to be equal using this predicate up here, so unique removed one of them. Yeah, the 662 just here. So it's really interesting. You can specify your own definition for what equality means, and that's pretty important when you're working with your own data structures and classes and things like that. All right, so unique is very, very cool. Do remember to sort your items first. Okay, and another couple of things before we finish up. Another reason why you might want to use lists is because of integrity to your iterators. So whenever you add or remove an item from a vector, the integrity of your iterators is, well, it's gone, really. Yeah, you've got to make all of your iterators again, but if you add an item to a list, all of the iterators are still all good. And also, if you delete an item from a list, all of the iterators except that one item that you deleted, they're all good as well. Yeah, but that item that you delete, that iterator is invalid. Yeah, so if you're able to, you might want to set up iterators at hotspots, like the 50 iterator in my little race example. And yeah, you might be able to use those hotspots to insert and delete data really, really quickly. But I mean, how often does that come up? Not very often, but it might. Okay, and the last thing that I wanted to mention, a reason why you might want to use lists, is because you might want to store really large objects. And you don't want to copy around your really large objects inside vectors whenever you've got to move them. It's better just to swap a few pointers around like lists do. I think this is not a particularly good example of why you would use a list, because often if you're using vectors for really large objects, you would just use pointers to them anyway. Anyway, it might come up. Alrighty, so that's about all I wanted to say. So together these two videos, today's video and yesterday's video, I think make a better little mini-series than what I could have made by myself just yesterday. So please accept my humble apologies for yesterday's blunders, and thank you very much for pointing out these flaws. Viewers, you people are legends. Seriously, good on yous, good on yous. Continue your diligent observations over what I'm doing, and I think together we can really make a very decent programming channel. All the best. Adios.